Good morning, students. Nice to talk to you again. We get to work on week 5 this week, and our big topic coming up in week 5 is this idea here, margin of error. All right, so it's good to see your smiling faces. Nice to be here where you can actually see me too. Sorry about the glasses and how you're always going to see the glare, but trust me, I'm glad to see you, and it's nice that you're here. So today, when we start talking about margin of error, there are some key ideas that we want to think about first, and we'll look at some examples and then how we're going to be able to calculate it and get some estimates of it. Margin of error, we just have to always remember, first of all, that no survey or observation or experiment that we're ever going to do is going to be 100% accurate, right? No matter what, this is still just a sample or a survey or a small collection of something that represents an entire population. And so if we can't tell the entire population, we know that there's going to be a little bit that's not quite right about the sample or the survey that we've done. Even when we have some things like the U.S. Census, where we ask every single person in the United States for their information, we do this every 10 years. It's part of our Constitution. We count every single person and we ask for data and information from them. But even that is not 100% accurate because there are people that they don't have addresses for or can't track down. We do try to make estimates of those people who are homeless or who didn't respond to the survey. And we also have people that are in constantly changing situations, right? They might have moved from one house to another, or they might have had a baby or had someone in their household pass away. And so even when we get that data from every single person, we might still be missing some data because it's constantly changing. So what we use is the margin of error to help explain or describe what we're going to call the wiggle room, right? That we give our data so that we know how confident we are in the final numbers that we're going to start using as our information. So we always want to have a little bit of wiggle room. That means we think that 80% of students love playing Minecraft, but we always want to have a little bit of wiggle room because it's probably not exactly 80% of students. So this wiggle room that we add, it's a range of values that tells us that the actual true population number that we're looking for, the actual percentage for the whole population, is somewhere within that range of values. So we may say, hey, we think it's right here in the middle, but the real number is somewhere in between these other two values, all right? Sometimes we call this a confidence interval. It tells us like how confident we should be in the numbers. So I want you to be familiar with that terminology too, margin of error and confidence interval. And when it's given, it's usually in the form of a plus or minus from the mean, okay, or from the data that they're actually presenting when they give us a statistic or a proportion. And so we'll see that this wiggle room, just like I'm kind of saying here, it tells you, hey, if we have a large margin of error, we have a lot of wiggle room above or below the information that we think that we're using. Okay, so let's see some of it in examples. We asked you guys to collect some data, and this is some information that some of my students put into their sheet. And so one of my students knows how much I love NPR, and so they found this statistic about should the government help fund National Public Radio. And so they have information about Democrats, Republicans, Independent, who said yes, who said no. And what we are focusing on here is this little part right down here. A lot of times we see margin of error at the bottom of the data or statistic that they're giving us. So this one tells us the margin of error is plus or minus 3%. So that means if we look at this line of total people, 39% of people said yes, government should stop helping fund NPR. And really, that 39%, because of this plus or minus 3% error, means that it could actually be as high as 39% plus 3, which would be our 42%. Or it could be as low as the minus 3 from there. So 39 minus 3, it could be as low as 36%. So this 3% wiggle room applies to each of these percentages. So the yeses could be as high as 42 or as low as 36, but we think it's around about 39. And the people who said no could be anywhere from 48% to 42%, but we think it's pretty close to 45% of the people said no. Here's another example of it. If there's support for minimum wage increase measures that were going on, this is a poll of people in South Dakota in 2014. And this one tells us, there we go, the margin of error right here is 4.37%. So the people who were for a minimum wage increase, it tells us that their numbers, their survey, had a result of 52% of the people saying they were for a minimum wage increase. But that number could be as much as 52.1 plus that 4.37 wiggle room that we need to add, or minus 4.37. So again, it just gives us a range of data, lets us know how confident we are. Okay. Now some of that stuff can really make a big change, because if we have here about half the people, if we said 50% of people or 52% of people agree with this measure, the state government might be like, hey, this is great. More than half the people agree with it. We should do it. But as soon as we subtract off this 4.37, all of a sudden that number doesn't look as fantastic as it did before. Because when we subtract off 4.37, the wiggle room that we need, we're only at 47.7% of people. So now all of a sudden, they don't have a true majority. What they have is a little bit less than half. So you see how this little bit of wiggle room can make a big difference. Here is another example of it. This one has our error margin here, plus or minus 3 percentage points. And so this one was asking about Democrats in Congress, if they're doing a good job, or who's taking a stronger leadership role, Democrats, or I guess this was George Bush, because this was back in 2007, right? So each of these values could be 3% off, right? Now that's a pretty big deal when you have something as close as right here, when we're at 44 and then 54%. If we're 3% off, these values could really change, especially when it's something that's very close like these. Because if it's 3% low, that could make this all the way up to 47%. Or if it's 3% high, this could be as low as 51%. And now all of a sudden those two numbers are not so far apart from each other. So here is an example we're going to look at from our lesson, and I know my image is kind of covering that up. If you have the lesson printout, we're looking at lesson 9, and we're in section 3 of lesson 9, section 9.3. So if you have this printed off, you might want to follow along with me. The example they gave us is a political campaign sends out volunteers into various parts of the state to get a sense of how well their candidate is going to do in an upcoming election. Election polls are famous for having this wiggle room that they apply. 30 volunteers each get a random sample of 10 people from across the state, and they find the proportion of people who are expecting to vote for their candidate. The sample proportions are summarized in this histogram. So we have 30 data points going on here. And if I added up each of these bars, remember we talked about like the area under the curve, this represents one of those data points. Remember, 4 of those data points are here. I'm saying between 30 and 40% are going to vote for their candidate. If we add up each of these data points, we're going to see that it's going to add up to 30, because there were 30 people that went out and took this survey and brought back their information and calculated their data. Okay. And it tells us that the mean of these proportions is 0.55, so 55% of people in total are expecting to vote for the candidate, and a standard deviation, remember that idea about what we consider still normal within this data, is 0.15. So it could be anywhere up to, let's see, if we're at 0.55 plus 0.15, we're looking at a 0.7, so there's one standard deviation, and down to 0.4, one standard deviation below the mean. Put that mu in there so you remember that that's like the mean that we're looking at. So for normally distributed data, about 95% of the data is within 2 standard deviations from the mean. We looked at that last week when we were looking at those percentages as we moved farther and farther out. So 95% of the data is within 2 standard deviations. This is asking us what percent of our sample proportions are within 2 standard deviations of the mean for these data points, right? So we marked on our graph up here where 1 standard deviation is, but I need to go a second one. So 0.7 plus another standard deviation of 0.15 would put us at 0.85, would put us right here. And going lower, if we were at 0.4 minus 1.5, subtracting another standard deviation off of that, would put us here at about 2.25. So that kind of cuts that bar right in half. Now I don't know this data point, like if it was 0.21 or 0.28, so I don't know where this one's going to fall down below. But if I'm thinking about it, we had 30 total data points, because there were 30 volunteers who went out and did this. And when I look at how many are within 2 standard deviations of the mean, 2 low and 2 high, we are looking at, let's see, there's 28, maybe 29. I can't really tell where this one's going to fall. But I'm going to go with the safe one and say 28% of those data points are safely within 2 standard deviations. And when I do that division, 28 divided by 30, I'm finding on my trusty calculator here that we're looking at 93% accuracy. That's pretty darn close to that 95% that we were looking at. If it was 29 up here, so if I did have 29, because I don't know that unknown data point there at the end, if it was all 29 here, if this one did end up being like a 0.28 and it fell within 2 standard deviations, then that percentage would be 97% accuracy. So when it asks us, what percent of sample proportions are within 2 standard deviations of the mean, it's one of these 2 numbers here, and does it match what we expect? I'd say yes, absolutely it matches what we expect. We are right there within that 93%, within 95%, within 2 standard deviations of the mean. We're going to stick with the same question, and now we're going to apply that margin of error. All right, so on our next slide we see still has that same information, and our margin of error, what they're saying, let's see, estimates for population characteristics are given with a margin of error. We've already seen that a couple times. It's the expected difference between the estimate of the population characteristic, the mean, or what we're normally finding, and the actual population characteristic, so from our sample and then applying it to the whole population. Okay, and so when we want to talk about being 95% accurate, right, to be reasonably sure that the actual amount, we want to be 95% sure that the population is going to match our sample that we took here. What we normally look at is that we use that margin of error, this plus or minus the margin of error. So I'm going to show you right there. There's that plus and there's that minus the margin of error. All right. And so the margin of error we should be giving with the estimates for that 0.55 mean if we want to be 95% accurate. Well, we saw before in our standard distribution curve, ooh, there's a terrible one there, sorry, still drawing right-handed here. And we had that mean right in the middle, and we could draw those dashed lines with the standard deviations. We were drawing 3 of them, each direction from the mean, right? And so we said that within that amount, between the first standard deviation was 68%. Within 2 standard deviations, we were saying was 95%. And within 3 standard deviations, we were saying was pretty much the whole population. It's really 99% accuracy there. And it's actually 99.7% of people are within 3 standard deviations. If we want 95% accuracy, that means we should be using this 2 standard deviation rule. Okay, so we want to go 2 standard deviations to be 95% sure that our number is within that portion. If we're okay with only being 68% accurate, we're only going to use 1 standard deviation. But we want to be more accurate than that. We want to make sure we're accounting for 95% confidence in our data. So we're going to use 2 standard deviations every time we do this for the purposes of this unit. Okay, so 2 standard deviations above the mean, and 2 standard deviations below the mean. Now, I already marked those on my other one, on my previous screen. And so we found that if we're looking at the low end, taking the mean and subtracting 2 standard deviations, that's going to tell us it's that 0.55. And we're going to subtract off 2 of our standard deviation values, and it tells me standard deviation is 0.15. And so that value that we found on the previous screen was 0.25. And again, we want to have that wiggle room going both ways. So not only do we want to subtract 2 standard deviations, but we want to add 2 standard deviations to the mean. Still using a mean of 0.55. This time we're going to add 2 standard deviations. And when we did that before on our previous screen, and when we do that here, we get a 0.85. So we can be 95% sure that if we polled everybody, if we actually had them vote for this candidate or not for this candidate, we know that the actual percent of people who would vote for this candidate is somewhere between 0.25 and 0.85. That's a pretty big range, right? If I'm running a political campaign and that's the best I can do, I'm not getting a lot of data from that, because knowing that I have between a 25 and an 85% chance of winning my election, I'm not feeling very safe. And so you might be asking yourself, well, how can we make that range, that wiggle room, a little smaller? And the way to do that is represented by this. It's by asking more people, right? The more people that we ask in our survey, or the more things that we sample, the more accurate our data is going to be. And so what this is showing us is, again, that idea that the more information we have, usually the taller and skinnier these normal distribution curves are. When we have more information, more data, a bigger sample size like we have here, we get a smaller standard deviation. We get people that tend to be really, really close to normal, because we can better define what normal is. Remember, that's what standard deviation does for us. It defines kind of what is the normal and how far outside the normal we are. And so the bigger the sample size, notice that the margin of error goes down. So does standard deviation. Okay? So the same exact kind of curve that's happening for standard deviation is also happening for margin of error. If we ask 2,400 people a question, our margin of error is so tiny, it's 2%. So that political candidate that was looking like they were going to win, like 55% of people were going to vote for them, all of a sudden now we have that from 55% with a 2% margin of error, we've got it down to 53 to 58. I'm sorry, 57. So if I'm that candidate, now I'm feeling pretty good. If I know I'm going to win 53 to 57% of the votes, I'm feeling like I'm going to win my election. And so I'm going to continue on with it. If we ask only a few people, and we get, asking only 384 people in our sample size, that margin of error is 5%. So that candidate that was going to get 55% of the votes, if we're thinking in reality it could be anywhere from 50 to 60% of the votes, well, I'm still feeling pretty good. It's only when we have a really small sample size like 96 that 55% of voters that I'm sure that I'm going to get, all of a sudden it might be as low as 45%. Or all the way as high as 65. This has a lot more wiggle room, and I'm really not sure where I'm going to fall within that. So you can see how the bigger the sample size, the smaller amount of wiggle room we're going to be giving people. Okay, so that's what these bars are showing down here. A pretty standard way to calculate what that wiggle room is totally dependent on the sample size. And so if we do 1 divided by the square root of n, our sample size, we can find out how many percentage points we need to give any data that we are able to compile from that. So if we ask something, and you'll see that a lot of these things are coming up very close to that amount. When I call up my calculator, doing that 1 divided by square root of the sample size is going to show me this information here. Calling it up, pulling it in here for you. Whoops. So using one of the sample sizes that they gave us here in the graph, I'm going to use this sample size here of 600 people. All right. And so a sample size, doing 1 divided by the square root of our sample size, 600 people, is telling me right there, that 0.04 is telling me I need about a 4% wiggle room. Okay? And that's actually what I see right here. Their sample size of 600 is actually a 4% margin of error. So that's where these numbers kind of came from. I don't want to think that they came magically out of nowhere. But using this 1 over square root of n tells us that the more number of items in our sample that we're taking, the better our data and the more accurate our data is going to be. Now, one last idea going on here. There is a much more complex equation about how to calculate margin of error. If you're taking AP Stats next year, you're going to discover it in that class. You can start taking lots of information about finding other accuracy measures, things like if we wanted to be 90% sure or 80% sure about our data, we can find all kinds of values there. But our big idea here is that the bigger the sample size we have, the smaller that margin of error, that bit of wiggle room that we have to give every piece of data. There's our lesson number 9. It also continues in our lesson number 11. So if you're looking for some practice problems, you can use lesson 9 or lesson 11 practice problems to practice our margin of error. Thanks, friends. See you soon.